So hello guys and welcome to a new video. Today we're gonna be implementing the DDPM paper explained in the last video. So as usual, go to collab, change the runtime type to T4 GPU. First we have the setup. So this is just the basic imports. Okay. Then we define our parameters, replicating exactly what was made in the paper. So 1000 time steps, 20 this is not a replication for the paper, just 1000 time steps and the betas. I'm gonna talk about them in a bit. 20 epochs, 128 batch size, and you can increase the number of epoch if you want. And you can change the learning rate and whatever. But the main ones are the ones over here. Now, in the last video, I said that we have only one beta controlling our generation forward process. However, in the paper, they use a different approach, and I'll explain why. You see, we agreed that we wanted a small beta. Now the question is, how small should our beta be? Now, as a reminder, we have alpha is 1 minus beta, and alpha bar is multiplication of all the alphas, all right? And our generation is basically we're shrinking each pixel by radical alpha bar and adding noise. Now, the problem is if we use like 0.02, we'll have an alpha of 1 minus beta, which would be 0.98. The multiplication of all the alpha t's at step number, when we apply this equation, at step number 300, around step number 300, we'll have pure noise. So we'll have xt is equal to approximately 0. And then from step 300 to step 700, basically we're doing nothing. So we can't have 0.02. At the same time, if we try like a really small one, like 0.0001, we'll have the alpha is 0.99999. The multiplication of all the alphas, even after 1000 steps, doesn't make us reach 0. So we're gonna have to have more steps. So in the paper, to like balance it and have like a model which within 1000 steps does that, they use the scheduler, which we will do later on. And the scheduler basically, like at the very first few steps, it uses a small beta. Then it starts increasing it gradually till it reaches 0.02. And that's the idea. In a later paper, which was called Improved DDPM, they used a cosine scheduler. Maybe we'll talk about it in the future. So yeah. Now, regarding the forward process, we already explained the equation in the last video. Just a small reminder. Basically, we shrink the previous image by, so we jump immediately from step 1 to the final step using this equation in the forward process. Basically, we multiply it by radical alpha bar, and we add noise to each individual pixel by radical 1 minus alpha bar. So yeah, how do we do that? First, let's make our betas. We use torch.linespace. Now, in case you weren't familiar with torch.linespace, it basically creates like an array of size t, where we start at beta start, which is in our case 0.0001. We end at 0.02, and like we calculate the slope and we increase the betas gradually till we reach the final beta. The alphas is 1 minus betas. Alpha bar is basically just a product of all the alphas. We calculate its square root. Then here we basically return a multiplied by x0 plus beta multiplied by epsilon, and yeah, that's basically it. And epsilon is sampled uniformly from 0, 1. Now, for the next step, what we're gonna do is we're gonna see how we can destroy an image. So we're gonna look at this block of code. Don't be intimidated by it. So for the first part, transform.compose. Basically, transform.compose is just a chain of operation applied in order. So the first one is to tensor. Okay, so the to tensor, it does 3 jobs at the same time. It converts the image to a tensor, reorders it to channels first. So we're using the MNIST dataset, which has a shape of 128 by 28 when we use to tensor, and then it rescales the images because the images are a number between 0 and 255 to a float between 0 and 1. So it does a transformation that gives each pixel, instead of having a number between 0 and 255 specifying how intense it is in black and white, it gives it a number between 0 and 1. Then we do transform.normalize. Now, if you hover above it, it tells you that we give it a list of means and a list of standard deviations. Here we give it a mean of 0.5 and a standard deviation of 0.5. So, so the idea is that we have an image between each pixel is between 0 and 1. If we take any pixel, so any pixel x is between 0 and 1, if we normalize it by subtracting the mean, so x minus 0.5, because here we have a mean of 0.5 and the standard deviation of 0.5. So if we subtract 0.5, here we have to subtract 0.5, we'll get a negative 0.5. And here we'll subtract 0.5, here we'll get a positive 0.5. Then we'll have to divide by the standard deviation. So negative 0.5 divided by 0.5, it becomes negative 1. And positive 0.5 divided by 0.5 becomes positive 1. So here we'll have each image between -1 and each image, every pixel of the image will be between -1 and 1. All right. Now, the idea is, like, you'll ask me, why are we going from 0, 1 to -1, 1? The idea is that we're gonna later be adding a Gaussian noise, and the Gaussian noise is centered around 0. If we have our pixels between 0 and 1 centered around 0.5, we'll be mixing a zero-centered image with a 0.5 centered image with a zero-centered Gaussian noise, which wouldn't work. The model wouldn't understand that. So we'll have to have them both be centered around 0, and that's why we made it between -1 and 1. Now, the MNIST dataset, we download the data over here, and we apply the transformations by giving it a parameter transform equal TF. Now, the DataLoader number of workers equal to, basically it spawns 2 subprocesses to decode and do the batching ahead of time. Yeah, and regarding drop blast equal to true over here as a parameter, basically it throws away the final short batch. So here we have 600,000 images divided by 128, which is our batch size. We'll get around 468.75. The last 0.75 images we drop it. So yeah, that's it. Now, we wanna destroy just one image, so I show you guys. So here I destroyed this image over here. As you can see, it gets destroyed at t equals 999. and at t equals 0, it's in its original form. How do we do that in code? So first, we take the training set. Each image is an image label. So we take the first one. So we take the first image, which is an image and the label. We just want the image. So we take just the first one. After it, why do we do unsqueeze of 0? Basically, okay, so this is not complicated at all. Um, basically, unsqueeze of 0, it adds at the beginning a batch dimension. All right. So we have an image of dimension one. Let me write the dimension 1 by 28 by 28. Basically, it's a 28 by 28 with just one color. All right. We want unsqueeze of 0. It says add an extra dimension at the start, which is just the batch the batch size. All right, so that's it. And basically, we're doing it because Q sample it expects a batch access. So if we don't do unsqueeze of 0, it will give us an error. All right. Now, basically, now we're so this is steps we want to visualize, all right? The figure size. Now, inside the loop, basically what we're doing, we take one element batch of time steps matching the one element batch of images, all right? So we do it over here, and so yeah, we take one element batch of time steps and we draw a standard Gaussian noise of same shape on the same device because here we're using the GPU. Then Q sample, it applies equation 4 over here. So we jump to the very last step and we just chose the image. So this is regarding the forward process. Now we're gonna talk about the backward process and training the network. So here we go. First of all, the network that we have over here, it's like as explained in the video before, its job is to look at a noisy image and predict what noise was added to it. Okay, so we do a unit. It goes from 28 by 28 to 7 by 7, and it does skip connections. And as I explained in the last video, one extra step is that we need to add which time step are we in. So we do sinusoidal embedding. All right. Um, so yeah, this is regarding the network, and now we're gonna explain the code in details. As I explained, it's just a unit with like time information. So the first function is a time step embedding function. Um, Basically, we're trying to add the time information. Um, so, um, First of all, uh, like if we try to add just a step as it is, like let's say it's at step 900. If we give 900 to the network, just add 900, it won't work. Basically because like the network is working on images between -1 and 1 with Gaussian noise between -1 and 1. Suddenly we passed 900. It's like we're like screaming at the at the neural network, you know. So that won't work. Uh, and So we have to give it a number between -1 and 1. And a single number, like it will give the network like nothing to work on. Um, so like from one single scalar, it can respond to t in a like a smooth linear way. But we want it like to tell apart 500 from 501, you know. So we try to add, so we try to do it like they did in the attention papers. And attention is all you need. Now, this line is just a fancy, numerically better way to, I just copied it out of the internet, of doing powers and dividing by 1000. So basically, it's just power of I over half. Um, Basically, we after here we'll get like a list of frequencies spaced geometrically, not evenly. First one is 1, and the last one is about 1/10,000ths, uh, and like they jump smoothly in between. So here we have the list of frequencies that we're working on, and basically we just do a sine, and for the even part, cosine for the odd part. Yes, that's it. Now, this is the unit, basically the same as the unit we implemented before. So we do conv.2d, then we do a res block. The res block is explained over here. Basically, we do normalization, convolution, um, and we normalize again, we do convolution again, we do skip connection, just like the unit video implementation. And it's basically the same implementation, just like the only thing that differs is that we add time embedding information. And yeah, that's regarding this block over here. Now, for the training loop, basically, just like in the paper, we take a real image, we pick a random timestamp, we draw noise, right? We build xt using equation 4, so we do the forward process. We jump from x0, the real image, to xt. Then we have our input ready for the network. The network has epsilon 0, has to predict the noise epsilon that we drew over here. And the network will take as input xt and t. So it will take the time step embedding, it will take xt, and yeah, basically that's it. So basically in every epoch, what we do is that here we take a random time step using the randint function. We draw epsilon to be in the same, and as I explained in the earlier video, epsilon is like drew for each pixel in the image. That's why here epsilon is torch.rand unlike x0. So it has the same dimension as x0. So each pixel, guys, focus, it's not the same random, it's not the same numbers that we sampled for all the pixels. No, each pixel gets a different number, and x0 is it's our image. Epsilon has the same dimension, with each one drew between 0 and 1, using normal distribution. So not between 0 and 1, drew using n01. And xt is basically q sample. So q sample is a forward function that takes us from x0 to xt. And then model of xt and t will predict the noise. And we calculate the loss as the mean squared error between the prediction of the model and the actual sampled epsilon. And again, the model over here is just a unit, exactly the same code. And the forward basically takes the time embedding and goes from 64 images of size 28 by 28 to images of size 7 by 7, and yeah, that's it. And here is the training loss, so we know that that it works for sure. By the way, one way to, I mean, here we're designing a simple network, but let's say you're designing a much complicated one. One way to do it is to train on just one batch. So we overfit it to just one image, let's say this image over here. And we should see the training loss like decrease. Now, in case it doesn't, it means that we have an error in the network. One way to do it is to visualize the gradient at each step of the network. And in the place where it's not going to zero, you'll know here, here I have a bug. But here we have a fairly simple network. Now, here we have the sampling code. So we start from pure noise and we start generating images. And basically, we use the network to predict how to unsample. And this formula gives us, as I explained in the earlier video, how to go to the previous image given the last image. So let's say we draw a noise. The noise is basically in the training step. Now we're finished training. Now we're sampling. The noise is equivalent to step number 1000. So we want to go back 1000 steps behind. At each step, first at x999, we have the noisy image. We have the network that predicts what the noise was, but actually, like, here we have no input image. So the network here is predicting what noise to subtract to get an actual image of numbers. And here we have the betas from the scheduler, 1 minus alpha bar. This formula will give us the value of the pixel of each individual one. Now here I did it in the code. So we go from step 1000 to step 1. Uh, here we have the t. Epsilon hat is basically what the model predicts as epsilon hat is the predicted noise. We should subtract the predicted noise but multiply it by beta t and divide it by radical 1 minus alpha bar. So we have to calculate alpha bar and basically that's it. Here I did it in the code, and these were generated from pure noise. All these images are images that started from pure noise. And here I wanted to make you see the steps where we go from pure noise to an image. So this is pure noise, pure Gaussian noise, and here are like random steps in between. Um, let me see. Yeah, random steps in between, and yeah, that's it. And here we have like a small summary at the end. Um, so yeah, basically that's a whole notebook. Okay, so the first example we showed was on the MNIST digits dataset, but I wanted to show like a more complicated notebook. That's why I picked the dogs one. So it's basically the same exact notebook, the exact same code. However, here we're working on images of dogs. One thing you have to note about the images of dogs, I'm not gonna go much into details here, but here you have, instead of just having one number per pixel, you have three numbers. You have red, blue, and green RGB to display the image. Here is the same Q0 forward function where we destroy the image completely. Now, for the unit from before wouldn't work here because that unit took us from 28 by 28 to 7 by 7. It wasn't very complicated, it wasn't very depthy. Here we also use the unit, however, we added attention. You'll ask me, why did we add attention? Well, for many reasons, really. Like, if we only use convolutions here, the convolution would only see a 3 by 3 neighborhood. So information across the image will not be seen. So for a digit, that's okay, but like for a dog, where the ears should be symmetrical, the eyes have to be the same color, like these fine details can't be really be caught by convolutions. And attention, it allows every pixel to read every other pixel in the image. And this like agreement between the pixels of the eyes would happen because of attention. Um, so yeah, now the same time step embedding function. the attention function. Well, the attention function over here, um, the attention function over here, well, what's basically it's doing, so from the attention is all you need video. We explained the Q, K, and V, the query, key, and value, neural networks. Basically here what we're doing is basically we're normalizing. Then one by one convolution is producing three separate vectors, which are the query, key, and value. And we flatten the image, and instead of having lengths by widths, we flatten it into n positions, so we would have n tokens, and thus we would have an image would become n tokens, and then we would dot every query against every key. We would get an n by n grid, and we softmax it to get the weights. And basically, yeah, we were doing normal attention. So each pixel would take a weighted average of all the value vectors. And at the end, we would reshape back to a grid, and we add to the input. So basically, we were just like doing attention. And the attention, we would be using it down in the unit down below. So the res block, the same res block as before. We do the exact same step from before. So yeah, you guys can read the code. Now, I by mistake, I restarted the training. Here you should do the training. It will take you a while. It should take you like 1 hour. The exact same equation from before. And here is sampling generated images of dogs. So I wanted to show how it's going with like 50 steps. So here we started from pure noise. We started removing the noise gradually, gradually, gradually. And here at the end, we had like a doggy at the end. And here I just like, in this block, I'm like generating many images of dogs, cute puppies, as you can see them over here. So I hope you guys enjoyed the video. I will be uploading the two notebooks. As before, if you have any questions, feel free to message me on my LinkedIn. I do propose that you try to implement these on your own. So if you have it just like for a lab project for your masters, don't just steal the code, try to implement it to learn how to use the different functions we explained today, and so you can implement papers in the future. And if you have any questions, as I said, feel free to leave them in the comments or to message me on my LinkedIn. Maybe I'll implement improved DDPM or one version of the improved DDPMs in a future video. And yeah, I'll see you guys next time. Bye.